So thank you for the introduction, and thanks everyone for coming here. So my talk today is about a unification of speed limit and Lieb Robinson bound with an approach of optimal transport. And this is joint work with Tomotaka Kuhara at Chiken, and who also give a talk tomorrow, and with Keiji Saito at Kyoto University. So this is outline to my talk. So first I will introduce some notion of speed limit, and then I will briefly explain optimal transport theory from which a unified speed limit will be derived. And last I will discuss two consequences of this unified speed limit. So there may be many notions of fundamental speed limit in our nature, but today I want to introduce two of them. The first one is called quantum speed limit on state transformation. So quantum speed limit tells us about the minimum time required for transformation between quantum state. And the second one is a Lieb Robinson bound on the speed of information propagation, and it provides an upper limit on the speed at which information can propagate in non-relativistic quantum system. So first I will explain what is quantum speed limit. So to do this, let me consider a closed quantum system with time-independent Hamiltonian edge, and the time evolution of the quantum state is given by this von Neumann equation. And for a given state phi 0, a fundamental question is how fast this quantum state can evolve to an orthogonal state. So for this question, in 1945 and 1998, it was shown that the minimum time required for this evolution between the orthogonal state is always bound by the average and bound by the variance and average of energies. So this means that the speed for changing quantum state cannot be arbitrarily large, and is always constrained by the energy of quantum system. And this inequality led to the notion of quantum speed limit, and subsequently it has been generalized to not only for pure quantum state, but only for arbitrary quantum state and for many other dynamics, including open quantum dynamics and even for classical system. And in general, quantum speed limit take this form. The operational time tau is only bound by some distance L between quantum state divided by maximal velocity. So metric L here can be, for example, Buret's angle or Fisher information metric, and velocity V should depend on the choice of the distance. And the second one is the Lieb Robinson bound. So to explain this, let me consider an one-dimensional quantum spin system with short-range interaction. So we have two local observable, A and B, which support a psi x and y separated by a distance dsy. So the Lieb Robinson bound say that the amount of information which quantified by this operator normal this commutator is always bound by an exponential term like this. So this bound means that velocity, speed of information propagation is always finite. And actually, this bound also demonstrates an effective light cone, linear light cone, that outside of this light cone, information exponentially decay. And actually, the Lieb Robinson bound has been well established for quantum spin system and fermion system for both short range and long range interaction. But however, for boson system is still under investigation. So the two notions of speed limit have been developed independently in the literature, and they have found many applications in various fields, and they have their strength and weakness. For quantum speed limit, it's a good point that the quantum speed limit tells us about the minimum time required for transformation between specific state. However, as we can observe we can see the metric error in the quantum speed limit is always order 1, which does not scale with the system size. So in general, for many-body system, the conventional quantum speed limit are not high, and can become trivial in the thermodynamic limit. The reason is the metric error in the conventional speed limit do not consider the geometric structure of the underlying dynamics. On the other hand, Lieb Robinson bound is very meaningful for many-body system because in the derivation of Lieb Robinson bound, the geometric structure, for example, the locality of the dynamics was considered. However, Lieb Robinson bound is a state-independent speed limit, so it cannot provide any information about speed of state transformation. So this observation lead to the motivation of our study. So it strongly desired to derive a unified speed limit that take both the advantage of the speed limit notion. So it is expected that such unified speed limit can uncover new meaningful limits that cannot be obtained so far. And our idea is to employ an approach of optimal transport. So to explain what is optimal transport, let me use an example of transport of goods. So suppose we have some goods made in factory and we want to redistribute them to some convenience store. And the distribution of goods at factory and store are given by P and Q. And a general way to do this is for any pair of factory and store N and M, we transport a fraction pi mn of goods from factory to store with a cost CMN per unit of goods. So by doing this, the total transport cost can be calculated by taking the summation over all the pair of factory and store. And actually, this total transport cost can be used to define a distance between distribution. And more specifically, everyone Wasserstein distance can be defined as a minimum overall total transport cost, minimum of total transport cost over all transport plane pi. And here's transport plane pi and Scott matrix C should satisfy the condition. And as you can see, there are many ways to define the cost matrix C. And actually, this is a very strong point of Wasserstein distance because we can include some useful information of dynamic into the Wasserstein distance through the cost matrix. So actually, the Wasserstein distance is a player key role in our study. So I want to move to the setup, a general setup in our study. So let G be an undirected graph with a set of node V and HE. And we also consider a vector state X with non-negative component. And this state evolves on this graph G. And the time evolution of X is given by this deterministic equation. So the chaining component Xi is due to the flow exchange between I and the neighboring node of I. And the flow should satisfy the anti-symmetric condition. And this ensures that the total sum of all components is always time invariant. An example of the vector X could be probability distribution in classical system or some vector observable in quantum system. And so for this dynamic, we ask a question how fast a vector state X can change. So we prove that the minimum time required for changing this vector state X is always bounded by the Wasserstein distance divided by the average velocity in terms of the cost matrix and the flow exchange between nodes. And I want to make some remark on this result. First, this unified speed limit is tight and can be saturated. So if this dynamic relies on optimal transport plane, so this equality can be attained. And the second one, this unified speed limit hold for a very general setup as long as the time evolution of vector h can be written in this form is always valid, and it's also hold for arbitrary cost metric. And actually, we can include the geometric structure of the dynamic into the quasi-time distance by properly defined the cost metric here. So it can be the cost metric, the information of a geometric structure can be included in the quasi-time distance. And as I will show later, the suitable choice of cost metric will lead to some very physically significant implication. So next, I will show two consequences of this unified speed limit. So the first one is called topological speed limit. So one of the simple ways to include some information of dynamics into the quasi-time distance is use the shortest path distance as a cost metric. So we can define the cost metric as a minimum length of the path that connect I and J in the graph. So by using this cost metric to define the quasi-time distance, we immediately obtain a speed limit like this. So reason we name this is topological speed limit because it encodes the information of graph topology of the dynamics. And the velocity now becomes the sum of the absolute value of the flow exchange between nodes. And I want to demonstrate some application of this topological speed limit. And one of them is quantum communication through spin chain. And let me consider a one-dimensional quantum spin system have a length of psi n. And the Hamiltonian is given like this, and the gamma is the interaction strength, and Bn is a parameter that can be controlled. And Alice have a quantum state encoded as spin on, and she wants to send this quantum state to the bulb at spin n by controlling the parameter Bn here. So fundamental question is how much time is needed to complete this task. So from the topological speed limit, we can prove that the time needed to transfer is always bound by the distance divided by strength of interaction. And this type of constraint on operational time cannot be obtained with the conventional speed limit. And here we show for one-dimensional system, but actually the result can be applicable to arbitrary graph of a spin. And of course, our result also can be applied to many other dynamics like chemical reaction network or a closed quantum system and open quantum system. So next we move to the second consequence of this unified limit, and it's the unified speed limit can provide a resolution of bosonic transport. So before explaining the second consequence, let me make some note on the Lieb Robinson bound. So the Lieb Robinson bound was completely resolved for spin and fermion system. However, it's still under investigation for boson system. And actually, in the case of short-range hopping, some Lieb Robinson bound have been derived for initial state with low boson density. However, in the case of long-range hopping, the problem is still very challenging, and it still remains to be an open problem. And to study Lieb Robinson bound, there are two problems must be addressed. The first one is speed of bosonic transport. So how fast boson can be transported from a region to another region. And the second problem is the speed of information propagation. And here we want to focus on the first one, which is speed of bosonic transport. So let me explain the problem setup of bosonic transport. So we consider boson system, which is a generalization of both Hubbard model on lattice, and in which Hamiltonian is given in this form, which has both long-range hopping and long-range interaction. So the first term is hopping term, which should satisfy a power law decay, which decay coefficient alpha is larger than spatial dimension d. And the second term is interaction term, which can be an arbitrary function of the boson number operator in this. So for this system, we are interested in the speed of macroscopic particle transport. So macroscopic here means that a number mu n of boson must be transported from x to y. So mu here is an order 1 constant, and n is total number boson. So that is the meaning of macroscopic. So for this system, it has been shown that if alpha is larger than d plus 2, so then the time required for this transport is always at least proportional to the distance dxy. So it means that a speed of macroscopic transport is always finite, even for every alpha is larger than d plus 2. However, this still remains an open problem for the full range of alpha is larger than d. And actually, our unified speed limit can resolve this open problem. So how we do that? So actually, we consider the vector boson concentration at each side. We define H is a concentration of boson at side I. And by applying our unified speed limit for boson system, and by defining the Cauchy metric in this form, which is the Cauchy metric Cij is always proportional to the distance between the side. So we can prove that the time is always constrained by the distance between x and y in this form. And actually, this bound is optimal because we can construct a protocol that achieves the same order of this bound. And our result completely resolves the problem of macroscopic bosonic transport in long-range boson system. So let me summarize my talk. So in my talk, we derive using an approach of optimal transport theory. We derive a unified speed limit that can include geometric structure of dynamics. And from that unified speed limit, we can have several consequences. The first one is topological speed limit that encodes the information of graph topology of dynamics into the quasi-Stein distance. And the second one is provide a resolution for the problem of macroscopic bosonic transport. And we have seen that many recent years as optimal transport theory has been applied to address many problems in quantum information, like Hamiltonian learning, quantum circuit complexity, and many other. So it would be very interesting to see whether our result here can be applied to solve other problem in quantum information and quantum many-body physics. So I'd like to end my talk here. So thank you for the attention.
Thanks for the nice talk. Do we have questions? Please go ahead.
So I have a question. You had this spin chain example.
Yes.
And you apply the topological speed limit to show like something like n over gamma. But it would also follow from the vanilla Lieb Robinson bound, right? Or does it do better?
Actually, the bound in some case of quantum communication through spin chain may not be saturated because we do some we perform some inequality from the topological speed limit to reach the simple bound on the time. So maybe it's not saturated, but it gives the in terms of distance. So maybe some factors is the bound maybe not high because maybe the bound is only the half time required to transfer quantum state. Sorry. Yes. So I mean, here maybe we should multiply here some factor. For example, it's maybe 2 or 4 to actually saturate this bound. Does this answer your question? Thank you so much.
All right. Further questions?
Yeah, as I saw, this was like essentially a classical result.
Yes.
And did you also think about like generalizing this with the different kinds of quantum Wasserstein distances that have been proposed in the literature?
Yes, it's very good question. Actually, yes, as you said, it's totally classical because we also use classical information, classical Wasserstein distance, and we also thinking about how to use some quantum version of Wasserstein distance to address the problem, other problem in the future. But at this time, we do not have any idea to exploit the quantum structure in the system because it's not trivial. I think it's difficult. Yes.
Hi, thanks for the nice talk. I want to ask about a general bosonic transport beyond the macroscopic setting.
Yes.
So,
yes.
like, what if you apply your method to that setting?
Yes. Actually, for microscopic transport, boson can be transported immediately if we only require to transport one particle. So such bound, the bound that proportional to distance may not be valid in the case of microscopic bosonic transport. So in the case of microscopic transport, there are some study in this year, I think in this year, put on a guide, discuss the problem of microscopic transport, and we have to do more some define bound on the momentum of boson number. And yes, our method cannot be applied to microscopic transport.
All right. More questions? Okay. If not, please let's thank the speaker again.